and today in this series of lectures I'll be introducing the idea of vectors because in H2 math this is a topic that many people struggle with, so I hope to bring it across as simple as possible, and we'll go from, in this series of lectures, we'll go from 0 to being able to find the closest distance from a point to a plane, and as well as intersections of some constructions. So without further ado, let's jump right into it. So vectors are simply is a topic in math that allows us to describe the 3D world. So you can see that the applications are immediate in fields like engineering, computer graphics, right, and game design. So if you're interested in anything that requires you to describe the 3D world in a structured manner, then vectors will be very useful in your line of work. So okay, so where do we begin? We begin by talking about points in 3D space. So for points in 3D space, how do you describe a point in 3D space? You describe it using 3 coordinates. One way is to describe it using 3 coordinates, and that 3 coordinates would be, as you know it, x, y, and z. So for example, you could say that point A is the coordinate. Point A is a point in space with coordinates 2, 3, and 1. Usually we denote points with capital letters. Yeah, and let's say we could also say another point B in space as the coordinates, let's say 1, 2, and 3. And so what this corresponds to is this diagram over here, where we see that A is 2, 3, and 1, and B is 1, 2, and 3. So these are coordinates in 3D space, and you can see that the red, blue, and green, they are the x, y, and z axis. So if you look at it from the red axis like that, then we see that it's a 1 corresponds to, you project it down to the x-axis, and 2 for point A, you project it down. So these are just distances along each axis. So yeah, so the x, y, and z just indicate the distance you move along in the axis. And yeah, okay, so sometimes you might also see it in another form, right, which is in the column form, and just note that they are pretty much identical, right? If you put in a column, then you're putting x, y, and z in a vertical format. So yeah, so that's all there is to talk about points, right? But there is a special point that we can talk about, which is the origin. So the origin is defined to be the point, usually we denote it with capital O, right? It's defined to be it's defined to be the coordinate 0, 0, 0. So in this case, we see that the center, where we travel 0 in all 3 directions, right? Travel 0 units in all 3 directions, that's the origin. So you'll see why this origin comes in useful later when we talk about directional vectors or position vectors. Okay, so yeah, so that's all to talk about points. So let's talk about vectors. So vectors, briefly speaking, is arrow. It's kind of like an arrow between 2 points. So what do I mean by that? Let's say we have the points A and B, right? Then we can draw an arrow from A to B. So what that will look like is, if we go to tools, more, then we can draw an arrow from A to B. So A to B will be an arrow. So if we take a look at it now, then we see that in the 3D space there's a arrow starting at A and pointing at B. So this is a vector is an arrow between 2 points. So for example, how to describe this arrow mathematically? So the vector, which we call AB with an arrow on top, right, to denote that it's a vector, will be equals to the coordinates of B minus the coordinates of A. So in this case, the coordinates is 1, 2, and 3 minus 2, 3, and 1. And so we come to our first lesson, which is how do we subtract 2 points in a sense. And the answer is we can do it coordinate wise. So we take the x coordinate of the first coordinate of the first point minus the x coordinate of the second. So in that case it's minus 1. And this one, 2 minus 3, we get minus 1 again. And lastly, we do it the same for the z coordinate, we get 2. So the vector A to B, right, described by this black arrow here, if we take a look at the algebra, the vector from A to B is minus 1, minus 1, 2. Okay, and GeoGebra is a tool that I use to plot this diagram, has automatically calculated for us the vector AB. So that is briefly what vectors is. So vectors is an arrow between 2 points, and it's also described by the XYZ column format like that. And what this vector corresponds to is, if we look from the x-axis, right, we focus on the red line, we see that the vector, the arrow from point A to point B, the vector pointing from point A to point B, the vector AB, when projected onto the x-axis, right, it moves 1 unit to the left. So it moves negative 1 unit in the x direction. And then we look at it from the y direction, right, so we look at it from the y direction like that. Then we see that the arrow AB, the vector AB in points is pointing negative 1 units, right, in the y direction. It goes from 3, it goes from y equals to 3 to y equals to 2. And similarly, if we look at the z direction, right, then we realize that it points from z equals to 1 to z equals to 3. So it points 2 units in the z direction. So that's how you describe an arrow, a vector, in 3D space by the x, y, and z as well. And it corresponds to the 2 points, right, the x, y, z and z coordinates subtracted from each other as well. So that's a vector. So yeah, so we previously talked about the origin. What is special about the origin? The thing that's special about the origin is that if we have, let's say we want to compute the vector OA, right, so we'll take the coordinates of A, right, minus the coordinates of the origin. So what that will look like is it will be 2, 3, 1 minus 0, 0, 0, which is just 2, 3, 1. So by virtue of the fact that the origin is defined to be the coordinate 0, 0, 0, right, any vector from the origin to a point, the vector from the origin to any point we choose will be just the coordinates of that point. So this is sometimes known as the position vector. So this is the position vector of A. Yeah. So do note that there's a key distinction between there's mainly a distinction between coordinates, right? Coordinates and vectors, and that is that coordinates, right? They are always from the origin. So it's like, for example, you have OA, so 2, 3, 1, or you have OB equals to 1, 2, 2, 3. And sometimes you write them in a format like that also. So 2, 3, 1 for A, and sometimes you write 1, 2, 3 for B. However, for vectors, it is between 2 points. So it's between 2 points. So for example, you have AB equals to minus 1, minus 1, 2. Sure enough, you could have vector OA, right, which is just between 2 points, just that the first point we go from is the origin, is 0, 0, 0. So in this case, yeah, so for vectors, it's between 2 points, but one of them could be the origin, whereas for coordinates, right, it's always starting from the origin. Yeah, so that's the relation between coordinates and position vectors as well. The position vector of any point is going to be precisely the coordinates of that point. Okay, so with that key distinction, we're actually done talking about vectors. Yeah, we're done with defining what vectors are. Okay, so now let's talk about different operations between vectors. So we can have addition of vectors. So addition of vectors. So let's say we have a vector AB, which let's just use the values from the previous example, and let's say we have another vector BC, and let's say that equals to, let's say 1, 3, 4. Okay, then what does this what happens when we add up these two vectors? So if we add up these two vectors, let's take AB plus AC, plus BC, then we are going to get minus 1, minus 1, 2 plus 1, 3, 4. And you can probably guess how we add up these two vectors. We add them up coordinate wise. So in this case, it's going to be for the x coordinate, it's going to be minus 1 plus 1, 0, then the y coordinate is going to be minus 1 plus 3, which is 2, and z coordinate is going to be 2 plus 4, which is 6. And this is actually the vector from A to C. So the reason why, right, so on the right hand side we have the arithmetic rule, with the arithmetic rule for adding up vectors, we have the numerical rule, right. On the left hand side we have the geometrical picture. So to understand vectors, it's always going to be an interplay between the arithmetic rules and the geometrical picture, and there's and you need to be able to understand both of them well in order to understand how to do the questions. So what do I mean by this? I mean that if we have 2 points A and B, right, I'll just draw them on a flat plane now, but just you must think of them as points in 3D space, right, and have points B and C. Then A and B will have a vector AB going from A to B, and then BC will be a vector going from B to C. So what it means to add up vectors, geometrically, it means that you are adding the arrows up, and how to do that is when you put the tail, the starting of one arrow at the ending of another arrow. So in this case, the vector BC, right, the tail of the arrow is at the same point as the head of the AB arrow, and when that happens and you add up the two vectors, then you get another vector AC that goes from A, right, goes via AB to B, and then goes from B goes to C via BC, and hence the net effect is going from A to C. So the first lesson we can take away is that when you add vectors, right, there's two pictures that you need to have in mind, two ideas, two understanding that you need to have in mind. One is the geometrical picture, which is just the adding up of arrows. And how do you add up arrows? You go from tip to tip. So if you have one vector like that and you add it with another vector, then the total, the sum of these two vectors will be like this. And the second picture you need to have is what happens when we do it numerically. If I give you two vectors in numbers, if I give you their components x, y, and z, then you add it up coordinate wise by adding up the x coordinate, the y coordinate, and z coordinate. So yeah, so for the reason why they are true, you can just think of them for each coordinate, right? If you move -1 in the x direction and then you move 1 in the x direction, then the net effect is that you move 0 in the x direction, and same thing for the others. So you move -1 in the y direction and 3 in the y direction, then the net effect is you move 2 in the y direction. So that's for addition of vectors. Okay, so yeah, so with addition, maybe you can ask, what if I subtract them, right? Can I subtract two vectors? And the answer is yes. And before we go on to subtracting vectors, let's talk about what it means to scale a vector. So yeah, so before that, let's talk about scaling, right? So you'll see why later. Okay, so for example, let's say I have a vector OD, right? So it's from point O to D, right? O being the origin. Okay, so it's a vector OD, and let's say it's equals to 2, 1, 2. Then what happens if I multiply this vector by a number? So let's say I have 4OD, or any real number. So in this case, we multiply by a real number. Then it's 4 of 2, 1, 2, and perhaps you can guess the most natural thing to do is to take this scalar and multiply each one of the x, y, and z coordinates. So in this case, 4 times 2 will give you 8, 4 times 1 will give you 4, and 4 times 2 will give you 8. So the x, y, and z coordinates just multiplied by the real number coordinate wise, right? So that is the arithmetic picture. But what is the geometrical picture of scaling a vector? The geometrical picture is increasing its length by the amount that you scale. So that's why hence the name scaling. So that means that you're essentially taking this vector and increasing its length by up to 4 times. So if this this vector had the every vector, right, a vector has a direction. Okay, so I didn't mention this previously, but a vector has a direction and it has a length. You probably learned this in physics. So if by scaling a vector by a real number, you're increasing its length, right? So scaling increases its length, but it keeps in the same direction. Okay, so that's the effect of scaling. So initially is OD is going to be 2, 1, 2, but at the end, OD, 4OD is going to be 8, 4, 8. So that's a geometrical picture of scaling vectors. Okay, so now one question is, can we scale vectors? I mentioned real number, right? So can I scale vectors by 0? And can I scale them by negative numbers? And the answer is yes, you can. So for example, if any vector OD equals to 2, 1, 2, right? So can have any vector, but let's just use the example of OD. Then let's say I scale it by 0. So this is the number 0 times the vector OD, right? So one is the letter O and one is 0. Then that will actually give me 0 times each of the coordinates, just give me 0, 0, 0. So you can see that by scaling it by a real number 0, I have reduced the vector of any possible length, right, into a 0 vector, which is just a vector of 0 length, which is just kind of a point. It's just 0. It's just the origin. And likewise, I can also scale a vector by a negative number. So let's say I have minus 1 times OD, then I'll get minus 2, minus 1, and minus 2. So what does this mean? This means if I scale a vector by negative, then it means that I'm flipping the vector around. So initially, we have the vector from O, the origin, to the point D. Then by scaling a vector by minus 1, I'm flipping it around like that. So this is minus 1 times OD, or sometimes we also write it as minus OD. So yeah, so this is going to be so if you see the coordinate wise, it also makes sense that if our vector originally went 2 in the x direction, 1 in the y direction, and 2 in the z direction, then by negating all its elements, I'm just going in the opposite direction. So the vector is just being flipped around. And in fact, if we check, right, that how do we make sure that this makes, let's do a check that if we take OD plus negative 1 of OD, then we're just going to get 2, 1, 2 plus minus 2, minus 1, minus 2, and that's just going to give us 0, 0, 0, which is the 0 vector. So in fact, OD, right, minus OD, it gives me, it cancels itself out, which is why this picture makes sense, because if we line the two of them up, right, then we are taking OD plus minus OD, and that just gives me the 0 vector. So that's for scaling a vector by a real number. Okay, then the next thing is we can now do subtraction with vectors. So what does it mean to subtract vectors? It just means if we have a vector AB minus BC, then it just corresponds to AB plus negative of BC. So what does this look like? This looks like if we have AB, let's say we have BC, then the first thing to do if we want to subtract them is we need to flip BC around. So then if we flip BC around, then this will be minus BC, and AB minus BC would then be this. So this is AB minus BC on the right hand side. So once we define the scaling of a vector, and once we understand what it means to invert a vector by multiplying it by -1 to flip it around, then we can do subtraction of vectors. So yeah, so subtraction is actually nothing special. It's just addition plus scaling. So it's just addition, but one of them we need to scale by -1. Alright. Okay, so now here's a quick segue into some properties of vectors. So you'll probably see this in the property list. So if a vector A, right, which sometimes so if you are referring to worksheet right now, maybe you'll see vectors denoted by a bolded A, and that also means a vector. So for example, A usually is the vector OA. So you see a bolded A, small, usually we denote it by small letters. It corresponds to, is another way of representing a vector. Yeah, and when you write it out, right, because it's difficult to write bold in using your hand, right, usually we'll denote it with a small tilde underneath. Yeah, so you see this in the question, but when you write it like that. Okay, so yeah, so that's just a notation. Okay, so now we'll talk about some properties of addition. Okay, so let's say A and B are vectors, and let's say lambda and mu are real numbers. So the first thing is that, let's say A, B, and C are vectors. So A plus B, right, plus C. So we put brackets around A and B. It actually corresponds to A plus B plus C. And if you go ahead and look at why that is so, is quite obvious from the addition of vectors definition. Likewise, you have commutativity, which is that A plus B is equals to B plus A. Right, so this is the associativity, and the next one is commutativity. Okay, then so there are some properties of vectors. The next one is scaling. So if we have a distributive property, so if A mu, if you have A plus B, right, so A is a vector, B is a vector, adding them up gives you another vector, and then you scale up by mu, which is a real number. Then it's the same thing as taking mu times scaling the vector A by mu plus scaling the vector B by mu. So this is known as a distributive property, similar to what we learned in algebra, that this one kind of distributes over the bracket. And likewise, you also have distributive in the other sense, which is that you have mu plus lambda. So if you have a real number that is constructed by adding mu and lambda, and you then use the real number to scale a vector, then that corresponds to scaling the vectors individually and then adding them up. So there's a few it's quite important to understand what happens when you're adding and multiplying. So when you're adding between two vectors, right, so you have vector A and vector B. When you add them, you get a vector, and yeah, and on the right hand side, so on the left hand side we get a vector first, then we scale it up. But on the right hand side, we scale up each individual vector, and then we add up the two vectors. So this is a vector, this is a vector, then we add the two vectors up, this vector addition, we get a vector. This entire thing is a vector. Okay, so yeah, okay, so that's briefly some properties of vector addition. So both of these are known as distributive property. So right now you might be yawning, you might be thinking, hey, commutativity is so obvious, or associativity is so obvious, but in fact you cannot take this for granted, because there are operations later on we see in vectors that are not commutative. For example, the cross product. The cross product is not commutative, right? It's a type of product between vectors, and and yeah, and as well as the cross product is also not associativity. So it's important to highlight these properties of vector addition. Okay, so now that we're done with that, let's pause the video and talk about the dot product in the next video.